All right, so let's get started. Today we're going to talk about UNet. It's a very powerful network. It was mainly designed for segmentation problems. So before we get started we touch base in the topic of UNet. I thought it would be best to briefly go over autoencoders. Well, autoencoders are not specifically discussed in this paper, and the authors they don't claim they get the idea from autoencoders, but I think understanding autoencoders will greatly help to grasp the idea of UNet. So typically, in your typical networks, we have convolutional neural networks, recurrent neural networks, and autoencoders. So in our typical convolutional neural networks, we have input as an image, and the output is a class, a probability distribution of a class that we are basically feed into the network as annotated data. The major difference between the typical convolutional neural network and autoencoder is that for autoencoder, we have input as image, and the output is same, image as well. So the basic idea behind autoencoder is that we like the network to learn the very principal idea features of the input, so it would be able to reconstruct the input again back as the output. So the main thing that drives the autoencoder makes it better is the minimization or optimization of the reconstruction error, right? So in the very high level idea is that here, if I can show it to you, annotation, here we go, is that here in this part we have our encoder hand, show that E, and this part we have our decoder, and this middle part usually called latent or code or bottleneck, right? So the encoder part, we are dimensionally reducing the input with whichever means we desire, depends on the application. We are narrowing it down and limiting it to a very smaller feature space than the input. So basically you're forcing the network to learn only the essential part of the input. And then from here in the decoder, we do upsampling. So it's called decoder upsampling or expansion. Encoder also called compression or downsampling, all the same names. And here by upsampling or decoding, we are basically reconstructing the input as again. So the main idea is to minimize this difference here. And so basically autoencoders are broken down into three principal groups: undercomplete autoencoders, regularized autoencoders, and the very distance relative of autoencoder is the variational autoencoder. This one is mainly used for prints like the basis of GANs, generative adversarial networks. Okay, so let's do this. So as I said, basically, depending on the application, you can change the component of your encoder and decoder. Let's say if you're dealing with words, sentences, vocabularies, you would typically use a fully connected neural network here and here to work with that application. If you're working with a time series, you would use RNN here. And relative to our topic, if you're using images, you want to do segmentation, we would use convolutional neural network. Convolutions here and here. So this encoder and decoder part is basically follows the typical procedure as we had before. We have a conv layer and max pooling for downsampling, and then here again we have conv layer and upsampling or transport convolution. Okay. All right, so in this picture, basically we have a convolutional autoencoder. We have an image 28 by 28, only one channel, and then we do dimensional reduction. We move it to 14 by 14 by doing downsampling, max pooling, and then but we are increasing the number of channels. So from 14 we go to 7 by 7, 3 by 3, and then in the latent space we are limiting it to only 10 nodes, right? And then basically after that we do upsampling 3 by 3, 7 by 7, 14 by 14, back to the original image here. So because we do flattening here, basically we are losing all the spatial features, all the localization features. Only we are focusing on the latent variables. All right, so moving on. A typical code for an autoencoder would look like this. So first of all, we do the pre-processing for the input, whatever we want to do. And then for the encoding part, we have our typical conv2d max pooling for this first layer, and then conv2 max pooling, conv3, and so on and so forth. And then here we have the encoder part. After that, in the decoding part, we do the upsampling, conv2d upsampling, Now it's better, instead of doing upsampling, because upsampling basically is the interpolation, it's better to do transpose convolution, so it can be trained. Very same procedures as you do your CNN networks. And then at the end, we would define our model autoencoders. So the idea is to minimize the decoded and input image reconstruction error. Yeah, so moving on, focusing on the middle layer, the latent space. First of all, I think this is the part that is basically important if you want to understand UNet. So what is latent space? Imagine you have a, first of all, latent means hidden. So imagine you have a paragraph filled with different words, all describing maybe a very same idea. Like you could have sailboat, yacht, steamer, cruiser. These words, they all basically, you could basically put these under the category of ships or boats. So this is the latent space. It's a very, the hidden layers, it's a very like the general idea that you can group the other features in your input. Imagine if you have a n by n matrices, let's say it could be so many different features in your input, you could limit that to k. K is called the latent factor. So you could basically reconstruct the original matrix by limiting it to a smaller amount of features. So basically you're grouping all the similar features in one row or a column. So the way it works is, let's say we have a very basic autoencoder, only one layer, like input and the output and the latent space here. We have transitions of phi and psi, where we want to move from our input space to the feature space, and then from feature space to the output space, which is the same as the input space, right? And the goal is to minimize the difference between these two. So this is the input and the output after going through the transitions. Same idea as you probably know already. We do we apply the linearity to the input. So we have a weight, input, bias, and the activation function. So we move to the hidden, the latent space, and then from latent space we have another weight, bias, activation function, and we get the output. So putting it back to the loss function, and basically putting this hidden layer into this part, and this would be the expression for our loss function. We are basically trying to minimize the difference between this and here by learning the weights and biases. It follows the same principle, like as a normal feed-forward neural network, we do backpropagation to find the appropriate weights and biases. So now the question is, so I said to learn the essential features, we are limiting the latent space to a smaller feature than the input, feature space than the input, right? So in this way, the network is forced to only learn the essential part of the input. My question is from you is that, what if the latent space had the same dimension as the input? What would that happen?
Sorry, yeah, so you can do with the same size, but then there won't be any image compression. That's what I'm saying.
Exactly. So yeah, so just to complete your answer, that's exactly correct. So if we have same size as the input or even larger, that meaning that our network is able to learn the same exact features as their input or even more. Basically what we have done is we have created a copy paste, like we are copying and pasting here. It doesn't compress, it doesn't learn the essential. It's basically copying exactly the input, pasting it as the output, copying, pasting. It doesn't learn nothing. So
we can, in principle, we can also learn a larger representation, like your hidden size can be more than your input size. In that case, the representation that you learn will be more sparse. So in some applications, that may be useful. Yeah.
So that would fall under regularized autoencoder, not under complete autoencoder. So under complete autoencoder, in principle, we don't have any regularization factor in the latent space. It's basically we have a dimension, and every node in the dimension is active. But what happens is that in the next group of autoencoders called regularized autoencoder, we are adding a penalty to the lost function. So in this case, let me just clear this. So in this case, there is a similar idea as regularization we have in our CNN networks. We are penalizing the loss function. So as I explained, for the regularization part, we have three major groups. We have sparse autoencoders, denosing autoencoders, and contractive autoencoders. So what happens is that for the sparse autoencoder, the penalty we add to the loss function is the sparsity penalty. And what the sparsity penalty is, I'm going to get to it in the next part. Denoising autoencoder, what we do is basically to prevent the network to learn the basic identical copy, input and output. For the input, we make it noisy, right? We add noise to the input. Let's say we have this figure, we add noise to it. And then for the output, we have the not noisy image, right? So in this part, the network is forced to reconstruct basically make the weights in a way, learn the weights in a way that would be able to reconstruct the output as without noise. Basically, it's learn the principal components, principal features of the input that the normal noise doesn't affect at all. And then lastly, we have the contractive autoencoder. This is very similar idea as our regular, regularization L1, L2. I'm not going to get into the detail of this, but the principle is very similar. So what is a sparse autoencoder? So the goal is, if I move to the end of it, the goal is to add this penalty factor, the omega h, to our loss function. So F is the encoder transition, and G is the decoder transition. So we have the input, encoder, decoder, and we want to minimize the difference between these two. And we want to add a sparsity penalty here. So how do we do it? Just a very short probability refresher. We typically show a joint probability like this. It means that we are looking at the probability distribution master function that both x and y are true, or they're both on, they're both 1, right? And for marginal probability, we are only looking at one part of this joint probability. So imagine we have our distribution p, x, y, and then we sum up over all y instances, then we would get the probability of x. And and this one, conditional probability, these are just a reminder, we probably already know this. It's written like this. So we want to look at p of y given that we know x, right? It will be like this. So it's a joint probability p yx over px. And there's the most, basically the well-known Bayes rule theorem is that p of x given y can also be written as p of x times py given x over py. So having these in mind, so the marginal probability I have marked it as 1 and conditional probability as 2. Having these principles in mind, basically, let me just move this out of the way. Suppose we have our visible variables, basically the input as x, and the latent variables, the middle, the bottleneck as h. Using the first rule, we can write the marginal probability. We can write px equal to pxy all over all h instances. You take a log from both sides, and it would look like this. So using number 2, the conditional probability, we can write the second expression. Where is it? Okay, here we can write it as p of h plus px given h. And then to add sparsity, basically the whole point is we want to add sparsity to this, right? Because whenever x is on, we don't want the h to be on. We want to add sparsity to the h. So in this way, the network is only moving or only turning h on for the, not every single point in x. So to add the sparsity to this, we can add the sparsity to p of h. And how it's done, probability is basically a distribution. You could fit it into any sort of distribution you like, normal distribution or whatnot. We add it to Laplacian distribution. It's the Laplacian distribution sparsity is shown like with this expression. The absolute value adds the sparsity around it, and we use Laplacian because it's sharper around 0, so it adds more sparsity to the network. Using this expression, putting pH back into our original one, we get sum of lambda h all over all h instances minus a log of lambda over 2. So this is a constant value. Lambda is a constant. So the first expression, this part, is the only variable part that depends on the input, the network. And we denote this as the omega h. And finally, we add the omega h to the loss function. In this way, we are adding a sparsity to our px and h, the joint probability. Okay, so moving on, variational autoencoder. As I said, the variational autoencoder is a very far distance relative to basic autoencoders. Basically, this autoencoder, variational autoencoder, is used for GANs, the generative adversarial networks. And the way it works is that basically we use it as a clustering factor because we are learning the latent features. We are moving all the inputs into their bigger categories like this, right? These are actually numbers, so they're moved into the clusters. And what we do with this is we can create new instances. Let's say we have a very famous example is that we have a face of different people from different continents, And then using the latent features from those faces, we can generate a new face that doesn't exist. Basically, we take one feature from each cluster randomly, and how we take the features randomly from each cluster and how they're distributed, those are all different concepts. So resources for autoencoders, I found these resources to be very helpful. Specifically, the first one, I'm going to show it to you if I can. Click on this. Oh, here we go. This is a very helpful tutorial made by TensorFlow. It covers many basic ideas in the deep learning, specifically by providing codes in TensorFlow. So if you're using TensorFlow, I highly recommend this resource. It explains introduction to autoencoder. If you want to learn more, the Goodfellow book, chapter 14, explains about autoencoder. So it gives examples with the code, basic autoencoder as we discussed, and moving on, this second example is the denoising autoencoder as I explained. So we have a noisy input, and then we like to, the output is a not noisy output. Provides all the codes that you can basically create this autoencoder, convolutional autoencoder, and then here, anomaly detection. So I think Stefan is, if I'm not wrong, Stefan is doing anomaly detection. So it gives an example of how autoencoders can be used for anomaly detection. Here they use ECG data. Basically, you can use any other data, EEG and whatnot. The principle behind anomaly detection using autoencoder is that you train the network using normal signals all the time. You put all the normal signals into the network, so it learns how normal is. And then once you put an abnormal signal, basically the reconstruction error is going to go high, right? So you put a threshold for the reconstruction error. This way, the network is able to detect the anomalies. Anyway, so I thought it would be helpful to share this resource with you. Moving on. Okay, let's get to the paper, the actual paper. So before we dive into the paper, I thought it's interesting to look at the timing of this paper. It was published in 2015, but if you look at the citation for the main author, it didn't really get much attention. Let's see, where's my pointer? Okay, it didn't get much attention till 2018, and it blew up basically in 2019 and 20. So it was published here. And I think anything, it indicates that how much segmentation object detection has grown just very recently. The attention has shifted toward these areas just recently. And also it could be part of the delay in getting recognition. It could be that the authors and the institutions aren't as famous as other institutions like Google, Facebook. That when they put out a network, it immediately gets attention. Yeah, anyways, so moving on, in the introduction part, the authors, they start talking about the other current methods for segmentation, mainly sliding window setup. So what is a sliding window setup? So imagine you have a picture, right? And you want to detect what's in the picture. Sliding window setup is a very common method used in most image processing techniques. It's not very specific to machine learning or deep learning. What you do is basically you have patches, right? And then you start scanning the image, going right down everywhere for the features, and then you learn those features inside the patch. And then you move on with increasing and decreasing the patch size, right? And this way, you're basically covering the whole image, and you move on one patch at a time. So yeah, so and then they talk about the pros and cons of the sliding window technique. Is that basically it can localize because you're moving in the spatial domain, and they also mentioned a second pro. They use a higher number of patches instead of images. That's one benefit for a sliding window. So in terms of the cons, the disadvantage of this method, they argue that because they have to go one patch at a time, it takes a long time, it's very slow, and also because they have to use different sizes for the patches, sometimes patches overlap, so that adds redundancy to the network. And lastly, they argued that there is a trade-off between localization and classification accuracy in these networks, because when you basically for the localization, you want to have a small patches, because you want to narrow down into as tiny as bit, so you can basically localize the pixel that is a cat or not, right? But for the classification task, you want to have larger patches, right? So you're taking more contextual information within a patch, so you can learn more features. So that's a trade-off. Like when you there's like a sweet spot for the patch, but if you increase or decrease the patch size, then you're basically trade-off in the accuracy for localization and classification. All right. So before we move on to the next part of the paper, I thought it would be better to give a very tiny bit additional information, background information, introduction. Basically, computer vision tasks are broken down into, first of all, you have the typical classification task. This is a cat or not, yes or not, right? And then you have classification with localization. Some people categorize this under object detection, some categorize it differently. In this section, in this classification localization, you only have one class, and you draw a bounding box, very rough bounding box. It's not very accurate. Why is it rough? Because basically you're trying to detect the centroid of the object, and then you have learned the typical aspects of the object, the width and the height of the object, so you draw a bounding box around the centroid to hopefully include the entire object. And lastly, the object detection is when you basically have multiple classes, they're overlapping, and you want to detect where they are, each of them are. For the classification, typical procedures, you split the input, you have your convolution, and then you downsample, max pull, activation relu for the middle parts, and the sigmoid softmax for the last layer. And then you repeat, convolution, downsampling so many times. At the end, you have your, classification. Classification localization, as I explained, only one class, one object. And object detection, I already explained this. So more modern approach to computer vision is you have image classification, sheep, dogs, what is in the picture. You have object detection, as I explained before, but you could also have semantic segmentation, is when you basically classify the pixel down to the pixel, each pixel. What is this? If this pixel is a shape or is a human? And then you have your semantic instance segmentation. You know these are shapes, but you can also distinguish between each instances. And these are typically done using the same principle as I explained in autoencoders. You downsample and then you upsample. So this way, the network can learn all the features down to the pixels. Okay, moving on with the paper. In the next section, they say the method is on the basis of a fully convolutional network, reference number 9. And they claim they made changes to the fully convolutional network in a way that it requires less training images and it outputs more precise segmentations. So what is fully convolutional network? Here in this paper, it's the original paper for fully convolutional network, submitted, published in 2014-15. So imagine your regular classification architecture, right? You have your convolutions, and then you have your fully connected layer where you basically try to figure out the class of these features you have, and then you can detect it at the end. What is it in the picture? So imagine we take this fully connected layer, right? And we substitute it with a one-by-one convolution. So what is one-by-one convolution? Is basically reduction in the feature space, not the dimensions. Here we are dimensionally reducing the image or the features, but one-on-one basically reduces in the feature space. So you are doing what basically we were doing in the autoencoders. We are reducing the features to the latent feature space. Only the essential features. That's how we are learning the image here. So once you do that, same principle as autoencoders. Then you upsample. In this way, because you have already learned the latent features of the image, like these pixels, they belong to dog. So these pixels, they fall on the category of dog. These pixels, they fall on the category of cat. So when you upsample, you basically can semantically segment the image according to the hidden features. So basically, this is a fully convolutional network. So what they did in UNet, the innovative part of it is, they're like, okay, this is working fine, but why don't we expand the upsampling part? So upsampling here, it's just, what's it called? It could be a transpose convolution. So it's a one-layer transpose convolution, or yeah. So they're like autoencoders, why don't we expand this part, make it larger? This way we can increase the localization feature aspect of the network. They also add other changes to this basic principle network that makes it UNet. I'm going to talk about those changes. Okay, so in this UNet structure, first of all, the basic principle of UNet is that you downsample and then you upsample, same as autoencoder. But how you do it and like what you do to the input, how you interpret the output, those are differ significantly. And to be honest, the original unit structure that is called vanilla unit, it's rarely used now. It has been changed so much. So basically, the results and the basic principle discussed in this paper for like the tiny details of unit, it might not be relevant nowadays. So how they do it, for the input, rather than padding it at the convolution layer, they mirror the border parts around the input. They don't really talk about the benefit of this. Like they don't really compare it to the padding. They claim it works better because for the border regions, you will have a complete convolution. The way it works, the yellow part, the convolution in yellow part is estimated by going over the blue region. But in the blue region, these parts are added later on. These are the mirror parts of the inside. You see the symmetry. Yeah, so but nowadays most unit structures they just use padding at the convolution layer. They don't use the mirroring. What else? So they also, two other important factors in this paper, they use excessive augmentation. They discuss it. They're like, we use excessive augmentation, and most importantly, they claim in biomedical imaging, elastic deformation is the most useful augmentation. What's elastic deformation is when you basically you grid your image and then you shift around like this. Right? This is the annotation part. This is the original image. And lastly, they claim that in medical images, we have so much overlapping. The cells basically are touching very closely. We have very tiny background input. It's mostly covered by cells, and it's very hard to distinguish the borders, right? For those cells that are touching. So they basically added a weighted factor to the loss function to increase the value, the weighting value of these regions in the training part. So in this part, basically, they're trying to improve the edge detection for the cell. So in the next part, I'm going to talk about how they basically do that. I think that's an important feature for this network, is they add this weight function to the loss function. So they add this weight factor to the loss function. And it's composed of two primary parts. The first part, WCX, is the frequency of the classes. This is used to compensate for the class imbalance. As I said, in the imaging parts, the biomedical imaging part, we mostly, especially for the cell, when you take a picture, microscopic picture of cell, it's mostly covered by cells. You have very tiny information coming from the borders and the background. This part is pre-computed from the ground truth. So basically, they trained it using the already known information to compensate for the frequency of the classes. The second part here is used to increase the value of the borders between cells. So how it's done, W0, they input a value for it, 10, sigma 5, they basically normalize the distance by 5 pixels. And this part, exponential raised to this D1 plus D2 squared. So D1, D2 is the distance of a pixel to the two nearest cells. Like let's say this is a cell, pixel, D1 to the border of the nearest cell, D2 is the distance to the border of the next nearest cell. So so simplifying this, we have 1 over e raised to the D1 plus D2 squared. I just noticed this is actually plot of 1 over x, not 1 over ex. 1 over x, it would pass the y. But anyways, it doesn't matter for our application because x here is only positive, it's a square. So imagine when D1 and D2, the distance from the two nearest cells, it goes down, like you are here in this region. This expression also, when it goes up, so we are in this region, this expression goes down. So the value, the weight factor for the loss, it goes lower. And then when we are at the border sections, this distance to the nearest cells go down, this value goes higher, so we have higher importance for the loss. And creating the weighted distance map, it would look like this. So these border regions, they have higher value. Okay, so this is basically the unit structure. How are we doing in time? Okay, I'll try to finish quicker. Very similar to autoencoder, as I showed you before. We have downsampling part here. So basically we have convolution layers here, here, and here. These convolution layers, we can basically change this. So nowadays, basically we have YOLO, we have efficient net, all these different structures. So basically you could change the backbone, these convolution layers of UNet with those new newly designed networks. It doesn't have to be, same as the original proposed network. And so you have convolution, downsampling, convolution, downsampling, convolution, downsampling. And same as autoencoder, you have upsampling, convolution, upsampling, convolution, upsampling, so on and so forth. So they actually crop. Also, so another feature in UNet is skip connections. So the reason they have the skip connection is because when you downsample, you come all the way here, you're losing features, especially localization features. So in this case, they're actually adding the last layer of the convolution in this level to the beginning of the layer in the upsampling part. So in this case, they're basically transporting the important features, specifically localization features, to the upsampling part. So the upsampling part is improving the localization aspect of the fully convoluted network. And okay, if you have any questions, feel free to ask me. A typical code for UNet, it would look like this. So you basically do the pre-processing to your input, whatever you have to do. You change it to the floating domain, and then for the contraction path, downsampling path, you have your typical convolution layers 2D. So we have 16 features or 16 filters. We are convoluting it using a kernel size of 3 by 3. Activation, we are using Relo. Typically for the middle layers, activation Relo is used. And then kernel initialization. Paper suggests us to use a Gaussian normal distribution. Same thing goes here. HE normal is a normal distribution, but it's truncated from the both sides, so it doesn't go to infinity. And then instead of mirroring, we use padding. And so basically, after that, we have dropout 10%, and then we have dimension reduction part. Max boolean is red arrows. So we continue all the way down to here. So once we want to move to the expansion path, that's the upsampling part. So we do the upsampling. Rather than upsampling, we do convolution transport. So it's preferred because we can actually learn in this convolution to transport and concatenate. So we basically stick the output of the downsample to beginning of the upsample. This way we are transferring important localization features. Same thing as the other part. We do convolution again, dropout convolution all the way to the end. So the idea is same as autoencoder. Idea is to reduce the error between input and output. And because here we have classes, so we basically map to our different classes we have in segmentation. So this link is another resource for UNet code. It's a YouTube link. The person goes over UNet structure, but in the description part of the video, he has his link to the GitHub repository where you can find many different variation UNet codes.
Excuse me.
Yeah.
Can you show the gray arrows in the code?
The skip connections? Yeah.
Yes, yes. The gray arrows.
This, yep.
Yes,
yes. In the code, okay.
Yes, yes.
Yeah, so it's a concatenation, this part. Yeah, so,
okay.
So what you do, U6 and C4, right? So remember, U6 is the expansion, right? So let's say this is U6, this blue part, right? And C4 is the crop section inside this part. You basically stick the crop section of the downsample layer to the beginning of the upsample part. And the reason they do cropping is because, as I said, in this picture, they didn't use padding, they did mirroring. So they had those extra layers around the input. So to compensate for that, they only take the inner side of the image. They do the cropping. So inner side of the feature map.
Yes, thank you.
Yep. Okay. So moving on. Let's see. So basically, this is the meat of the paper. And after that, they talk about the results, the competitions. So we already talked about all these parts. Separation, the weight factor for the borders, data augmentation. So here they talk about the results from participating into three different segmentation tasks. I mean, it's good to go over the results for this paper, but it's not really relevant nowadays because, as I said, the very basic UNet structure is rarely used. And also UNet is a very established architecture, so I don't really need to prove it. It's been shown that it's a very effective segmentation model. So in the results section, they use 3 different data sets. All 3 different data sets involve cells. I think one very big weakness for this paper is that they claim that they have introduced very effective biomedical imaging segmentation tool, but they only focus on cell structure. I think biomedical imaging goes beyond cells. You could have so many different tissues or parts. You could have teeth, you could have arms, skeletons. So mostly this, I think this network is very specific to the domain of cell microscopy. So I think the title and the claim the author makes are somewhat misleading. So yeah, so basically they covered a bunch of different cells, and they reported the error values comparing to different other method techniques. For the first part, they reported wrapping error and rand error. Wrapping error basically only focuses on the topological aspects of the image rather than the pixel-wise, the geometric errors. So let's say you have a like a feature like this, right? And then you reconstruct it. If I can draw this again, right? So this has very little wrapping error, but if you reconstruct it and then you enclose it here, you have this continuity here, like you have this continuity here, then the wrapping error goes higher because it only focuses on the topological differences. And then you have your then you have your rand error, basically focus on the clustering aspects of the reconstruction. Where are the most of the pixels clustered around what part? Yeah, and then the next two data sets, they also report the accuracies, 92% compared to the second best one, 83%, 77% compared to the second one, 46%. Yep, that's basically UNet. If you have any questions, feel free to ask me.
Thank you. In the last sentence of section 3, they said that the dropout layers can be considered as implicit data augmentation. Can you explain that?
Yeah, so when you have dropout, you're basically throwing out part of your feature map, let's say 10%, 20% of your feature map. So you are basically, the end result could be somewhat considered as, because you're randomly throwing out information in dropout, so that the end result is like, as if you're adding noise to your image. It's a part, like an augmentation.
Yes, thank you.
Yeah, next time, if I get to talk, I'm gonna discuss how we can mix UNet with different structures, how we can change the convolutional layers of UNet, let's say using a more modern approach, such as efficient net. So next time if I talk, I can talk about efficient net and how it can be incorporated in UNet. Thank you, Brad.
Thank you so much.
Thank you, everyone. So I'm gonna stop the presentation here, stop sharing.